Good morning, champs. In this video, we solve a classic creeping flow problem in cylindrical coordinates. Viscous flow between two rotating cylinders. The goal is not only to obtain the velocity field, but also to see how the governing equations simplify in Stokes flow and how cylindrical geometry affects the solution. We consider two concentric cylinders filled with a viscous, incompressible fluid. The inner cylinder has radius r1 and rotates with angular velocity omega 1. The outer cylinder has radius r2 and rotates with angular velocity omega 2, which may also be 0. The fluid occupies the region between the cylinders. Our objective is to determine the velocity distribution in the fluid. Because the geometry is circular, we use cylindrical coordinates r, theta, and z. The velocity components are u(r), u(theta), and u(z). We start from the governing equations for incompressible Newtonian fluids. First, the continuity equation. The divergence of the velocity equals 0. Second, the Navier-Stokes equation. Density times the material acceleration equals minus the pressure gradient plus viscosity times the Laplacian of the velocity. We now simplify the equations step by step. First, the flow is steady, so all time derivatives vanish. Second, we assume creeping flow, meaning the Reynolds number is much smaller than 1. In this regime, viscous forces dominate inertia, so the inertial terms can be neglected. The Navier-Stokes equations therefore reduce to the Stokes equations. Next, we consider the symmetry of the problem. The system is axisymmetric, so nothing depends on the angular coordinate theta. There is no motion in the axial direction, so uz equals 0. There is also no radial flow because the cylinder walls are impermeable. Therefore, ur equals 0. The only remaining velocity component is the tangential velocity u theta, which depends only on the radius r. We now check the continuity equation. In cylindrical coordinates, the divergence contains three terms: a radial term, an angular term, and an axial term. Because ur is 0, the derivative with respect to theta is 0 due to axisymmetry. And uz is 0, all terms vanish. Therefore, the continuity equation is automatically satisfied. Next, we use the theta component of the Stokes momentum equation. For the tangential velocity, the viscous term becomes the second derivative of u theta with respect to r, plus 1 over r times the first derivative with respect to r, minus u theta divided by r squared equals 0. To solve this equation, we multiply everything by r squared. The equation then becomes r squared times the second derivative of u theta plus r times the first derivative of u theta minus u theta equals 0. The general solution of this equation is u theta of r equals a times r plus b divided by r, where a and b are constants. We determine these constants from the boundary conditions. At the inner cylinder, the fluid velocity must match the surface velocity of the wall. Therefore, u theta at r equals r1 equals omega 1 times r1. At the outer cylinder, the velocity equals omega 2 times r2. Substituting these two conditions allows us to solve for the constants a and b. The final velocity field therefore has the form u theta of r equals a times r plus b divided by r. The first term represents solid body rotation, where velocity increases linearly with radius. The second term represents a vortex contribution, where velocity decreases with radius. The real flow between the cylinders is a combination of both effects. This example illustrates an important feature of creeping flow. When inertia is negligible, the governing equations become linear and often reduce to relatively simple differential equations that can be solved analytically.